Okay, good morning, everyone. Let's start for the X-ray diffraction chapters. And let's start from the properties of X-ray. And actually, this is the first chapter of this book, this textbook, Elements of X-ray Diffractions, written by Carletti. Okay, and again, as we just know from the geometry and structures of crystals, and also how to index crystals. Then let's move on to talk about X-ray diffraction. We will first talk about the properties of X-ray, and followed by diffraction series, diffraction intensities, diffraction masses, and practical applications for SRD analysis. So in summary, we just know the crystallography. So we know about the importance of crystal structure on the materials properties. So let's now learn how to use X-ray diffraction to explore crystallography. Okay, let's talk about X-ray. For the history, X-ray was discovered by Röntgen, and then it was named because of its unknown nature at that time. And actually, X-ray is very special compared with the light. It is invisible. It can travel in a straight line, and also it shows very high energy. And because of its high energy nature, it is more penetrating. Okay, just like the X-ray pictures we will see the bombs, right? And X-ray have a dual wave particle character, 波粒二象性. So it can be reconsidered as electromagnetic radiations. So we can see it as a wave. So it will have a wavelength, and it has a range for 0.5 to 2.5 angstrom. So you can see this. This is the electromagnetic spectrum. We can see that this shows different units, like for the frequencies. We can also represent it in photon energy or wavelengths. So you can see that actually the X-ray is here. It is composed of hard X-ray and soft X-ray. So as you can see here, with a smaller wavelength, it comes to gamma rays. Below them, we have ultraviolet, 紫外线, and visible light, and IR, right, 红外线. Okay, so we still can consider it as a particle, so we call it photon. So for this dual wave and particle character, it can be wave and particle. And for the nature of X-ray, it will not be affected by the electric and electromagnetic fields. And how are we going to produce X-ray? Now we know the properties of X-ray, so we can try to apply it in real applications. And the most commonly used method will be cathode ray tube, CRT. And for the mechanisms, actually it's very interesting. First, we generate high energy electrons. And when these high energy electrons have rapid decelerations, then there will be an energy loss. This energy loss, 99% of this loss will turn into heat, but the rest 1% will produce X-ray. So for the method, you can see a CRT here. So first, we use a high voltage electric field to generate electrons. So you can see here, this is our target, and this is our tungsten filament, 灯丝. So there will be a high voltage electric field here, and then it will generate electrons and it will move toward this direction. It will move from tungsten to our target. And for our target materials, it could be molybdenum, copper, and so on. In general, we use molybdenum or copper. So electrons will bomb into this target, that is molybdenum, and then it will experience rapid decelerations. So the energy loss will become X-ray here. X-ray will be all around, so it will produce X-ray for all directions. And as we said, 99% of energy will turn into heat. So we need to have cooling systems to cool the target. And also, because we produce electrons, right? Exciting electrons, which will bomb into this target. So we will require a vacuumed atmosphere. Vacuumed will be better for energy, for electron to pass through this region. And as we said, 99% of the energy will convert into heat. So we need to use cooling systems. And for the high voltage, it needs to be at least 30K to 50K volts to generate high energy electrons. And vacuum is used for accelerate electrons so that it can bomb into the target. And the target, which is anode, must be metallic materials because we need electron transition here. Okay. And let's talk about continuous spectrum or wide spectrum. So we now know that once we have a high voltage electric field, then accelerating electrons will bomb into our target, that is the anode, and it will form X-ray. And here we can see a continuous spectrum. That is because X-ray is actually composed of different wavelengths. As we can see from previous electromagnetic spectrums, it has a range like to 0.5 to 2.5 angstrom. That's for the wavelength of X-ray. And why would it has different wavelengths? That is because we know that electron must experience decelerations, but not every electron experience the same degree of decelerations. So it will show different wavelengths. As you can see here, this is the wavelength and X-ray intensity profile. And the target is molybdenum. Also, we change for applied voltage. Okay, and then we see different plots, different distributions. And first, let's see this SWL, short wavelength limit. It determined the minimum wavelength that can be produced. As we know that if we have a smaller wavelength, we will have a greater energy, the greater energy for X-ray. Okay, so SWL is the minimum wavelength. So you can see that if we increase the voltage, let's say here from 5 to 10 to 15 and 20, this is k volt. You see that it shows a decrease for SWLO values. So the X-ray energy will increase. And also you can see here for the intensity. If we increase the voltage, we can see that the maximum intensity will increase too. Okay, let's talk about more for continuous spectrums. In previous slide, we know about if we increased the applied voltage length, then the X-ray intensity will increase. But here we know that actually this X-ray intensity will also depend on the atomic number in a proportional relationship. In other words, if we choose materials with a higher atomic number, then we can get higher X-ray intensity. So that's why we choose a heavy metal like molybdenum for the target. And for this material selections, actually it will not affect the wavelength distribution of X-ray. That is because of its mechanisms. The mechanism for a continuous spectrum is the generation of X-ray. And X-ray is composed of different wavelengths because the electrons experience different degree of decelerations. Okay, if you choose different materials, they will show the same wavelengths and X-ray distributions. But of course, the intensity will be different, as you can see here. And here we notice a very important finding. That is the peak here. It occurs for this 25 kV, but it has not been shown for the voltage below these critical values. So it seems that if we try to increase the applied voltage to a certain degree, then we will see a characteristic radiation. We call it 特征辐射. Okay, so it must be under a higher enough voltage. So in the next few slides, let's talk about this characteristic radiation or the spectrum. Okay, so for the characteristic spectrums, it means that we have a specific peak formed within the continuous spectrums. And it must be when the applied voltage exceeds critical values. This will be different for different elements for different materials. So we call it characteristic radiations. And for the nature of it, it shows a very high intensity and narrow in the wavelength. As you can see here, this is the peak for K alpha and K beta. You see the peak here has a very narrow range in the wavelength, and so also show a very sharp peak. That is the high densities. So it will be very useful for us to use it for characterizations. So we use this for the real applications of X-ray. Because if you continuous X-ray, it will not be useful because it has a different wavelength and also the intensity is not as high as that for the characteristic X-ray. And actually, it will fall into several sets. For example, K, L, and M, with increasing wavelengths. Okay, with increasing wavelengths, but only K lines will be useful. That is because for the wavelength M, it will show a higher wavelength. For K, it shows a smaller wavelength. But X-rays will fall into this K regions for a smaller wavelength because this is kind of closed to the atomic distance, atomic radius. So in general, we use K lines. And here are the questions. What are these symbols? K, L, M, and maybe here K alpha, and also K alpha 1, K alpha 2, and K beta. So it would be related to the quantum mechanics. And this is actually a review for the quantum mechanics. So we have two models. One is a Bohr model or Bohr atomic model, and the other one is wave mechanical models. And for Bohr model, actually, electrons are assumed to revolve around the atomic nucleus in discrete orbitals. So that fall into the regions for quantum mechanics. Okay, and the position of particular electrons is well defined. We will call it quantized. Quantized. So for the energy of electrons are quantized, and the electrons have specific values of energies. It will be on the different energy level or energy state. Okay, and this is just to let you know how to define the energy. And as a summary, Bohr model treats electrons as a particle with specific orbitals. However, for wave mechanical models, it treats electron as both particle and wave. That's the dual wave particle characters. Okay, so the position of electrons are described by probability because we consider it as a wave. So you will have an electron cloud. Okay, now we know some about quantum mechanics. So let's talk about why we have this K alpha, K beta, and maybe the K, L, and M. So first, let's see that because we have X-ray production, right? And X-ray production, it will form this characteristic if we have a higher enough voltage. And the reasons, so first, during the production of X-ray, the continuous X-rays, so accelerating electron will bump into the target. And when we have a higher enough of the voltage, it will have a higher enough energy for this accelerating electrons. It will knock off the electrons of the target inside. It means that the electron inside, just like this Bohr model, maybe this ones, will go out. And then, because the inner side shows a stable configuration, so the electrons outside must go in. And for this energy transitions, it will produce X-ray here. Okay, so this is what we call characteristic spectrums. And why we need to have a critical applied voltage? That is because we need to have a certain values to knock off the electron inside these shells. Okay, and let's talk about the K, L, M, and also K alpha, K beta here. So K, L, M actually they refer to the principal quantum number. So K is for n equals to 1, L is for n equals to 2, M equals to n equal to 3. And K alpha means it moves, okay, as we see here, electron will be knocked off. So if the electrons will, the electron that was being moved on the K shell, so the other electron must go inside to fill the vacancy, right? So if we fill the K shell vacancy, we call it K. So K means from somewhere to K. K means from somewhere to K. L means from somewhere to L. And alpha means the close, the closer one. So L means 4 for one share. If 4 to K, it will go from L, this is alpha, like L to K or M to L, just for one share. But beta means 4 for two shares, like here, M to K, okay? M to K or N to L is for two shares, okay? M to L, M to K. And how about alpha 1 and alpha 2? We know about K and alpha, right? What about alpha 1 and alpha 2? So actually it involved subshare. So for Bohr models, we did not see the subshare. We must see the wave mechanical model. So we know that we have the subshares. For example, like 2p or 2s. And let's talk about more for this. Now we know about, for example, like K, L, and M, right? K, L, and M. And actually, for K, it has a higher energy, the higher energy. So it will be the smallest wavelength. And how about for the alpha and beta, and alpha 1 and alpha 2? Actually, you can see here. This is the K alpha and K beta. And for the intensity is about the probability. For alpha and beta, the probability for this alpha one would be more likely, but for the probability for beta one would be not likely. Let's say that again. What is alpha and what is beta? Alpha means from the near shared, it moves only for one share. Beta, it means it moves for two shares, so more likely for alpha. And how about alpha 1 and alpha 2? You can see here. It's kind of complicated here, so let's just say that for the intensity, alpha 1 will be higher than alpha 2. Okay? And if you need to know, actually the value of this intensity for alpha 1 is 2 times of alpha 2. So alpha 1 equals to 2 alpha 2 around. And for the wavelength is about energy. So you can see here, for this is K alpha and K beta. K beta shows a higher gap for the energy here. So higher energy for beta. So the wavelength would be smaller for beta. Okay, and alpha 2 and alpha 1, you can see here the gap for alpha 1 is larger. So higher energy for alpha 1. So it will be lower or smaller wavelength. And you can see the results here. Let's see here. This is K alpha and K beta. K alpha has a higher intensity than beta, right? Higher intensity. And then for the wavelength, alpha has a higher wavelength. So you see on the right hand side, beta is on the left hand side. And how about alpha 1 and alpha 2? So alpha 1 has a higher density, as you can see here. And alpha 2 actually has a higher wavelength, as you can see here. Okay, and let's talk about more for characteristic spectrums. And actually for the frequency or the wavelength of these X-rays, it depends on the atomic number of the target. As you can see here, this is a Moseley relationship between a square root of V and Z. Z is for atomic number, and V is for frequency. So you can see here, if we increase the frequency, we get a higher, sorry, it should be the reverse side. If we increased the atomic number, so you can see for these directions, we will see an increasing frequency. Increasing frequency means a smaller wavelength. And here are two notes here. If we change the applied voltage, it will affect the intensity of a characteristic X-ray. Of course, because the intensity is about the number of photons. But for the wavelength, it will not change because the reasons why we will have characteristic radiations is due to that it bombard the target, and then the electrons for outer shell must be filled in. So it's about quantum mechanics. So the energy, the quantum state will not be changed for different applied voltage. So it will not change the wavelength. And the second note is the characteristic radiation actually share different mechanisms for the continuous radiations. So for characteristic radiation is due to the electron transition in atoms, and for continuous radiation is due to the decelerations of electrons. And now we know about the characteristic spectrums. It shows a very high intensity and narrow in the wavelengths. So actually we can use it for our machine like XRD. This could be used as the source of XRD. And also, this is just a profile, so you can know that this is a typical SRD profile. It shows a different structure or elements. This is the appearances for this equipment. This is a D2 phaser. We will learn about how to use this equipment. And also, this characteristic spectrum can be used for elemental mapping, EDAS mapping. So we just learned about the Mosley relationship. We have a different frequency and atomic numbers. So different frequency, it could have different wavelengths, and of course different energy. So you see here, this is the energy, and for different elements, it will show a different peak for different energy here. So we can identify the atomic percent or weight percent for the elements. This is the EDAS in SCM or FIB. Okay, let me make the summary for you for the continuous and characteristic spectrums. So, for the mechanisms, the continuous spectrums, the formation of this spectrum is because the decelerations of electrons, and because not every electron experiences the same deceleration degree. So this spectrum shows different wavelengths for the X-rays. But for characteristic spectrums, it is because if we have a condition that with a higher enough of the applied voltage, then this accelerating electrons bombard the target. It will also cause the electron transition in atoms. These transitions will produce X-ray. This is what we call characteristic X-rays. So we just know about that. This X-ray would be discrete for the wavelengths, but for continuous, it's just continuous. And for the wavelengths, about the effects of applied voltage. If we have a higher voltage, the wavelength will decrease, right? Short wavelengths, okay? But for the characteristic spectrum, it shows no effect. This is about the quantum mechanics. And for the intensity, both of these two will have a higher intensity for higher applied voltage. And if we increase the atomic number of the target, intensity of this X-ray will increase. And for this, it shows not a result for the intensity. And if we increase the atomic number, the wavelengths will decrease. Okay, the wavelengths will decrease because the different materials have a different characteristic spectrums. Okay, and because we have a smaller wavelengths, if we have a higher energy. And for material selections, this is a similar concept. It shows no effects on the wavelength and intensity distribution. But for characteristic one, it shows a different one for different materials, like you can see here for the wavelengths. And let's talk about absorption behavior of X-ray. So now we know that how we produce X-ray. We first use high energy or accelerating electrons. The bombardment on target, that is the interact between electron and atoms. It will produce X-ray for all directions. This is for continuous spectrum. Okay, and during that time, at that time, X-ray will partially transmissions for the materials and partially being absorbed, okay, by the material, by the matter, 物质. So it's about the interaction between X-ray and atoms. So you see here, it's different. And now let's talk about concept we called mu, linear absorption coefficient. And for this absorption coefficient is actually proportional to the density. So let's first try to see these equations. So Ix is about the intensity of X-rays after passing through a material with a thickness x. So we know that the intensity go out for this thickness, it will be reduced, right? So this one is the reduced intensity. And I0 is the initial intensity. So this will be higher. This will be lower. Okay, so let's talk about this mu. This is about the absorption coefficient. Linear is means we estimate it from one dimension. Okay, and also as we know that this is about the density of the materials. So we can just try to use this mu over rho. So this has nothing to do with the density, but we need to give it a rho here. Okay, so we can rewrite this with these equations. And for this one, okay, this should be wrong. The linear absorption coefficient is mu, and for mu over rho, we call it mass absorption coefficient. And then actually we have an equation for this three: mass absorption coefficient, atomic number, and wavelength. This is mass absorption coefficient, atomic number, and wavelength, and K is a constant here. So we can see that if we have a decreasing wavelength here, we get decreasing mass absorption coefficients. So we have a higher penetrating depth. Okay, so as we know that X-ray has a small wavelength, so X-ray is penetrating, different from light or the other electromagnetic radiations. X-ray is penetrating. Okay, and let's see that with a nickel absorbed 吸收的物质. This is an example. If we have a nickel absorbed, then we will observe a phenomena we called absorption age. We will have a look from this. Let's first go through this text. Okay, it will exist because the high energy X-rays will excite electrons in shell, then it will produce a photoelectric effect. So photoelectric effect, it means we have transitions from light to electrons. So this is our radiation. The X-ray energy will transfer for electron energy. And first, let's see how it works from the right-hand figure. Okay, this is about the relation above energy and mass absorption coefficient and wavelength here. So as we know that for increasing from this direction, for increasing this is a wavelength lambda, right? Increasing wavelength, the energy of X-ray will decrease. Okay, and then let's try to see if we have a material, what we call nickel absorber, in the middle of this X-ray. That means this X-rays penetrate this nickel absorber. Then what will happen? So let's see the above figure. And the observation will be from right to left. That is the increasing energy or decreasing wavelength. Okay, let's see here. If we have a decreasing wavelength, we know that the mass absorption coefficient will decrease. As you can see here, it will continuously decrease. Then here something happens. There is a very sharp rise for the mass absorption coefficient. After that, it continues to decrease. So this is the first step. This is the second step. This is the third step. And the first and the third step refers to these equations. So let's talk about the second step. This is what we call absorption age, and the mechanism is shown here. But let's talk about it in more detail in the next slide. So first, we have, as we said, we move from right to left. That is the decreasing wavelength. So increasing energy, right? The increasing energy of X-ray. When this energy of X-ray meets the excitation energy for electrons in the absorber. Okay, let's say we have a nickel absorber. Then X-ray go in and out. So if this X-ray energy meets these conditions, for example, for K or share, then absorption age would occur. That's what we see in previous slide. Okay, and what is the excitation energy? It means that we have a stable energy for different electron configuration, right? We have a 1s, 2s, and 2p. Electrons fall in and become stable state. And then we have X-ray energies. It may bombard, then the electron will go away. Okay, so that's about the excitation energy. So electron go away. This is the photo electron effect. So as you can see here, because this is the mass absorption coefficient, we follow the equations. If we decrease the wavelength, this mass absorption coefficient will decrease. But once we meet the excitation energy, it will show this absorption age. So this is for LO, and we have three different types. This is about the subshare. And after that, we have K here. And for K, it will be very hard because K is very stable. It's the closest in the share, in the nucleus. So you need a very high energy. That is a very small wavelength to have a K, excitations. Okay, so this is how we said here. For inner shed, K is very hard for excitation. K would be very hard for excitations. And this is just a supplementary material to let you know that actually for materials or matters, it can absorb X-ray in two ways. One is called scattering. One is called true absorption. That is what we said here. So this is the two ways that the X-ray go in and out. We know that the intensity will be decreased. So this is what we said. It will absorb X-ray, but we have two different mechanisms. And for the interactions between X-ray and matters, we will have three types: scattering, absorption, and diffractions. For scattering, it's about Compton effect. We will not talk about it here. Absorption is what we said here. And for diffraction is the key concept in this course. We will discuss it in the later chapters. Okay, and this is just a review for the mechanisms. As in this chapter, we talk many physical behaviors. For example, like continuous radiation, characteristic radiation, and also absorption age. Let's talk about the mechanisms as a review. So for continuous radiation, it's about the accelerating electrons bombard the target. After that, these electrons will experience decelerations, and this will cause X-ray production to form a continuous spectrum. And for characteristic radiations, again, we know this accelerating electron bombard the target. But if we have a higher enough voltage, it will also induce electron transitions. Okay, electron transition in the target. So this is for electron transition in the target. But this electron decelerations is for the input. This is our input, right? From the tungsten filament. Okay, so once we have electron transition in the target, it will form characteristic X-ray. And for absorption age, once we form high energy X-rays, and then it will go out. If we go out and meet a materials, it bombards that materials we call absorber. And then this X-ray energy is higher enough to meet the excitation energy for the shares. Then it will show the electron excitations in the absorbers. So the mass absorption coefficient will rise rapidly. So this is the three mechanisms for three different physical behaviors. And the last two pages, let's talk about filters and X-ray safety protections. Actually, for filters, it's based on the concept or knowledge for absorption age. As we know that if we have absorption edge, we have increase for the mass absorption coefficient. It means that the X-ray penetration depth would be decreased. Okay, as you can see here, this dash curve is for the absorption edge for nickel for these materials, and that this is for the intensity of characteristic X-ray. If we double, we put this overlap these two together, what we will see? Because we have decreasing wavelengths here, and then after this point, here shows a very large absorption for the signal. So we see that the intensity here will be very, very low because the nickel absorber shows a very high effect for absorptions. But here, because there is no absorption edge, so the absorption coefficient is small. Okay, so we can try to remove the X-ray signal. We can use this nature to remove undesirable X-ray signal. Okay, and for the notes here, we choose filter for the materials one more or less atomic number than the target materials. So this is for the copper target, so we will choose the nickel filters. Okay, for example, for copper target, we choose nickel filter. For molybdenum target, we choose zirconium filter. Okay, and for X-ray safety, we know that X-ray could be dangerous. So for the protections, we must choose a heavy metal to protect us. And heavy metal is because heavy metal has a higher atomic number, and we can see it from this equation. This is the intensity, right? After transmissions. And actually, if we have a higher atomic number here, it can give rise to a very small intensity for transmissions. Okay, so this is the mechanism how we are going to use this knowledge to protect us. So in general, that is very useful. It's very easy to get and has a very high stability at room temperature. So that is used to protect a human from the X-ray. Okay, I think that's all for this chapter about the properties of X-ray. And thank you for your attention.